Problem 5. Let points A, B and C lie on a circle gamma. Circle delta is tangent to AC at A. It meets gamma again at D and the line AB at P. The point A lies between points B and P. Prove that if AD is equal to DP, then BP is equal to AC.
So the battle in this question is to draw the diagram. Once you've drawn the diagram, it isn't too bad. Now, if you start by drawing the triangle ABC, you may get yourself into trouble. It turns out to be easier to draw the circles first. So, I've drawn a couple of circles, gamma and delta. I know, or I'm told, that the intersection points of these circles are A and D. And you have to make a choice. So I'll let this one here be A, and this one here be D. Then you have a line which is tangent to delta at A. So you'll have a line like that. And that hits gamma again at C. You have another point P on delta that is equidistant, that AD and PD are supposed to be the same length. So imagine having some compasses in your head, sticking the pointer in at D and swinging the arc round so that you'll get something distance, the same distance from D as A is, and it'll be something like that down there. And then A, P, and B are on a straight line. So your diagram looks something like that. And we're lucky, A has fallen in between B and P, as was required in the specification of the problem. In fact, the result is true, irrespective of the order in which the points A, B, and P lie on that straight line, but the method turns out to be different, and we wanted everybody to attack the same problem using the same theorems. So that's why we've specified the order like that. Right, now we need to make some progress and work out what we're trying to do. We're trying to show that the distance AC and the distance BP are equal. Well, it makes sense to draw in other relevant lines. So I'll join A to D and D to P. Those lines have the same length, remember? Right. Now, I'll draw in C to D. It's terribly tempting to think that that's a straight line, but it's not necessarily. Okay, so you imagine there's a kink there. Probably you're going to draw in BC and maybe BD. Looks like a useful line to draw. And that gives us plenty of geometry to play with. Now remember what we're trying to do. We're trying to show that PB and AC are the same length. We've got some data already. We know that AD and PD are the same length. Looks as if triangles, congruent triangles might be in play here. Let's do a bit of angle chasing and see what we get. So I'll introduce an angle down there, call it alpha. We've got an isosceles triangle with apex D, sides DP and DA, so that angle's going to be alpha as well. Now, angle in the alternate segment, classic GCSE mathematics. We've got a tangent line to a circle. So the line CA is tangent to the circle delta, and so this angle here will be equal to the angle in the alternate segment. That's another alpha. Now focus upon the circle gamma. Angles in the same segment subtended by CD. We have an angle alpha here. That means we have to have an angle alpha there as well. Lots of progress. Let's introduce a new angle. Let's have that be beta and work with angles in the same segment in the circle gamma. The angle B is subtended by AD. Well, I called it B, I meant beta. Similarly, over here, you'll get a beta. So they're subtended in the same segment. So we might have some congruent triangles in play. Let's have a look. There's a triangle with angles that we know, alpha and beta. That's triangle PBD. Then there's another triangle with the same angles in it, alpha and beta. So that's triangle ACD. Now, two of their angles match up, and their third angle matches up as well. So these are definitely similar triangles, because angles of a triangle sum to 180. And you've got this common side length sitting in the same place between the corresponding pairs of angles. So these two triangles are congruent. ASA, angle, side, angle. But that will do nicely, because BP and AC are corresponding sides in these congruent triangles, and so they must have the same length. So here's another way of approaching the problem. With geometry questions, there are usually lots of ways of approaching them. So there's something called spiral similarity, and I'll explain what that is. When you've got two similar figures in the plane, they needn't be anything particular. They could be triangles or smiley faces or anything, but they must not be parallel to each other. So it's not just one is a translation of the other or an enlargement of the other, but they're in sort of general position. What I've drawn here are a directed line segment from blue to red and another directed line segment from blue to red. Now they're clearly similar directed line segments. The theorem says there is a point in the plane about which you can rotate and then enlarge and carry one line segment to the other. And moreover, there's exactly one point of the plane which does that, and it's called the center of spiral similarity. There's even a neat way to find it. So what you do is you look at the lines defined by the line segments and you see where they would meet. Well, I won't draw it, but if I produce that, it would happen about there. Now you draw a pair of circles. The circles both go through this black point I've drawn there. One of them goes through the two red points and the black point. The other one goes through the two blue points and the black point. Right, so let's try and do that. It's going to be tricky, of course. So through the two red points and the black point, something like that. Now through the two blue points and the black point, something like that. Now these two circles, the red circle and the blue circle, cross at least once. They cross at the black point, but they therefore cross somewhere else. There. And that turns out to be it, the center of spiral similarity. Can you imagine using this as a kind of pivot? You would rotate this directed line segment around this pivot until it was up here and parallel to this line segment. And then you would enlarge, or in this case, shrink from the center of spiral similarity and bring the large directed line segment down until it was superimposed upon the shorter directed line segment. That always works. You can look up theory in books and on the internet. So if you're interested, please go and do that. I'll now show you how this theory enables you to solve this BMO1 problem. So I've drawn the diagram of the problem again. but the circles have acquired colours. We're interested in showing that the directed line segment PB has the same length as the directed line segment AC. So let's instead investigate the spiral similarity that carries one to the other. Now, the two lines defined by PB and CA meet at A. So this point here is the black spot. It's the point where the two lines cross. It's also a blue spot because it's the tail of AC, just as P is a blue spot because it's the tail of PB. So B and C both have red spots because they are the noses of these directed line segments. So let's draw the circles. We draw the circle that goes through the two red spots and the black spot, which is here. So that turns out to be circle gamma. Then we need to work out the circle which goes through P, A, and the black spot. But the black spot and the blue spot are the same. So at first sight, you've got a problem because you've just got 2 points and they don't uniquely define a circle. So the way you deal with this is you imagine that CA is just a tiny little bit shorter, so that it will keep its nose at the same place, but we will keep its tail, we'll make its tail move slightly towards C. The place where the two lines will stay where the blue spot currently is, and the new blue spot will be on this line, AC, but a tiny distance down towards C. So I think you can see what you need to do. That is to say, amongst all the circles through P and A, you draw the one which is tangent to the line AC at A. Oh, and we've got lucky, that turns out to be the circle delta. So our diagram is in fact the spiral similarity diagram. The center of spiral similarity, bless its heart, is the second point of intersection of the circles. And we can rotate PB about D and then apply an enlargement from D and get AC. Now, what's going to happen is P is going to rotate to A, but the lines DP and AD are the same length. So an enlargement with scale factor 1 is required to finish off. So you don't need to do a rotation about D and then a non-trivial enlargement. You just do a rotation about D and then do nothing at all, or enlarge with scale factor 1. But that means that PB and AC have the same length. The scale factor is 1. So you're done. So here is a third approach. It uses some trigonometry. Now, those of you who are at GCSE level may not know much of this theory, so you can just ignore this or be fascinated by it and go away and read. It's your choice. The people in the sixth form should be in better shape. Let me remind you of the sine rule. You've got any triangle with sides A, B, and C, then these ratios, A over sine A, B over sine B, C over sine C, are all equal to each other. But that's not just the fact by itself. The interesting thing is not that they are all equal to each other. They are, in fact, all equal to something which is important, which is the diameter of the circumcircle of the triangle ABC, or if you like, twice its circumradius. The great thing about this formula is that it enables you to write down the sides of the triangle, their lengths, in terms of the angle. So for example, A is equal to 2r times the sine of the angle at A. And similarly for the side lengths B and C. So that means that since we've got lots of circles in our diagram and various lengths, we should be in a position to write down trigonometric formulas for various lengths. So let's do that. So first off, I'll put in some angles. I'll call that alpha and I'll call that beta. And I'll run around the diagram calculating some other angles. So the triangle DPA is isosceles. We've got this DP equals DA business. So that angle there is another alpha. We've got a tangent to a circle. So CA is tangent to the circle on the right. That means that angle in the alternate segment applies. And this angle in here will be alpha. Anything else? Well, this angle here, angle DAC, will equal to angle DBC by angles in the same segment. And down here, ACD will be equal to the angle ABD by angles in the same segment. So we've got another beta there. And we've got something else which is quite interesting. We've got a cyclic quadrilateral, ABCD. And we've got an exterior angle to it. So this angle in this whole angle there will be equal to alpha. So if I subtract beta from it, I get the angle alpha minus beta there. There's another angle which turns out to be useful, which is this angle here. The angles of a triangle add up to 180, so this is going to be 180 take away 2 alpha. And the neat way to say that is that it is the supplement of 2 alpha. Put a little S up there in the exponent. So stare at those angles and make sure that you agree. Right, so here are 4 significant lengths in the diagram, and let's see if we can write down trig formulas for them. AP, well, that's a chord of the right-hand circle, and it's opposite the angle 2 alpha. So, well, 2 alpha supplement. So the value of this will be twice the circumradius of that circle, which I define to be little r, times the sine of the supplement of 2 alpha. But the way that sines work is that the sine of an angle and the sine of the supplement of the angle are equal. So we can forget about that supplement nonsense. So we're in business. AD. Well, that's a chord of 2 circles. It's the chord of the right-hand circle. So it is equal to 2r sine alpha. But it's also a chord of the left-hand circle. So it's twice capital R times the sine of beta. This is great, this fact, because it enables us to trade off little r and big R. We can eliminate one of them. What about AB? Well, it's a chord of the left-hand circle, and so it is twice the circumradius of the left-hand circle times the sine of the angle which it is opposite. And what about AC? Well, that's another chord of the left-hand circle, so it's equal to 2r times the sine of alpha plus beta. Now, at this point, these formulas take over. We don't need the diagram, except to remind ourselves that, let's make a careful note, that BP is equal to PA plus AB. And we want that to be equal to CA. So I put a question mark underneath that equation. So that's our ambition in life. So we can forget the diagram now and do some trigonometry. Okay, so what I'm interested in is is showing this equation to be true, it will be enough to look at the difference of this length CA or AC and PA or AP. If they differ by AB, we're in business. We've established this equation. And we've got formulas for various things, so let's apply them. AC is twice capital R times the sine of alpha plus beta. And AP is twice little r times the sine of 2 alpha. So I've used the formula for AP and the formula for AC. And I've got a trigonometric expression for their difference. I don't like the 2 times little r, but I can use this equation to get rid of 2 times little r, because 2 times little r is 2 times big R sine beta all over sine alpha. So I've simply used the expression for AD to get rid of the little r. Right. Now, if you know enough trig, you will know various formulas. The sine of alpha plus beta is given by the formula sine alpha cosine beta plus sine beta cosine alpha. So that's a standard A-level fact, and if you're interested, go and read about why it's true if you don't know it already. A special case of that is where alpha equals beta, and you get that way you get the expression for the sine of 2 alpha. So I need to subtract 2r sine beta over sine alpha times, well, sine of 2 alpha, it's going to be 2 sine alpha cosine alpha. Now there's trouble brewing. The sine alphas will cancel. And the term above, 2r sine alpha cos beta, we can't do anything about that. But this term down here is now 4r sine beta cos alpha. And we're taking that away from 2r sine beta cos alpha. And when you do that, something nice happens. That's 2r. This is unchanged, but this plus sign becomes a minus sign. But we can use that formula for the sine of alpha plus beta again, but replacing beta by minus beta and using the fact that the sine of minus beta is minus sine beta. You have to know this trig stuff. And so this is equal to 2r sine of alpha minus beta. But that's AB. And so we've established this equation. So the trigonometry has done it all for us, and we have another solution.